Then I'll introduce Blender. I'll show the difference between real-time and...
muting the whole thing, so...
In this video, we'll talk about the difference between regular data and big data in computational physics. Hopefully you'll be able to see the differences clearly. I'll start by talking a bit about myself. We'll talk about computational physics, then I'll introduce Blender. I'll show the difference between real-time and big data simulations. I'll describe rigid body physics and soft body physics separately. I'll show a series of cool demonstrations that illustrate these concepts, and lastly, I'll show some real-world applications of this technology. This is me. Since high school, I've been interested in physics, computer science, and teaching. I've created this video to appease all of my interests. I've used Blender to construct all of the virtual simulations that you see. It was quite fun, very challenging, and time-consuming. Hopefully I'll be able to construct some tutorials for some demonstrations so you can learn how to do them as well. Physics simulation is used in many design and engineering industries, and by association, businesses as a whole. Thus, I would be surprised if it doesn't affect your life. If that's not enough, scientists working within this field usually make a very large salary, which gets me very excited. This is an example of regular physics. It's a very simple demonstration of a ball falling to the ground and then bouncing repeatedly. This is the same demonstration in a virtual medium. A virtual ball bounces on a virtual floor. This is computational physics. Now we'll talk about Blender and meshes. This is Blender. In Blender, a mesh is constructed from a series of vertices that connect to make lines, which ultimately connect to make the faces that you see. Each vertex has an individual location in 3D space that allows it to create these intricate shapes. In Blender, a set of these vertices is called an object, which will have a location, rotation, and scale, among other much more complicated attributes. Moving on to physics. Real-time physics is often interactive. A perfect example of this is a video game which is playing in the background called Rocket League. You can see the ball bouncing off the car and the car rebounding as well. Big data physics is significantly more complex and impressive, like this simulation. This particle fluid simulation took nearly 6 hours to calculate for the 16 seconds of footage. The result is quite a real-looking demonstration of computational physics. Some of the larger simulations could take days, weeks, and even months to complete. Now that we know the difference between real-time physics and big data physics, we can talk about rigid body physics. With rigid body physics, all forces are applied to the origin of an object, which is usually located at the geometric center. On this object, I've moved the origin to the left of the screen, and you can see the odd effect it has when forces are applied to the origin of the object and it's not at the center. The advantage of rigid body physics is it has much lower computation time than soft body or fluid physics, and so larger simulations can be created. Finally, we get to some examples. This is a simple rigid body simulation that was calculated in real time. A series of balls are simply rolling down a slope with some obstacles in the way. There are only 86 objects in this entire scene, but the balls are quite complex, so there are 39,000 vertices. This simulation isn't terribly impressive. This is a similar experiment, except with a lot more balls. Well, technically these objects are tetrahedrons, but from far away you can barely tell the difference. This simulation has 6,158 objects and 74,000 vertices, which let it qualify as big data. Remember, the forces are applied to the origin of the object, so it's the number of objects that matters the most when regarding computation time. This second demonstration is basically just complex Jenga. The tower is hit at the bottom by a fast-moving ball, and eventually it falls down. There are 580 objects in this real-time simulation because the collision calculations between boxes are quite quick. This demonstration is one of my favorites. The tower is hit by a moving plank in the middle of the bottom, and eventually it's a point where the tower cracks and falls down. It's quite interesting to watch, and there are an astounding 9,300 objects in this simulation, which results in a quite spectacular demonstration. Now we'll talk about soft bodies. Unlike rigid bodies, soft body objects have forces applied to each vertex or molecule within the system. This results in a significantly longer computation time. Because of this complexity, there are many more options to play with. Creating these simulations takes much more effort, but they're very pleasing to watch. This is a molecular cube falling on a knife object I've created. It was computed in real time, and so it's not very accurate. There are 512 particles in the cube, it's 8 by 8 by 8, and it took about 5 seconds to calculate the entire simulation. This is the same simulation with a much denser and big data cube. The cut is significantly more clean, and as a result, I think the simulation is cooler to watch. In this demonstration, there are almost 43,000 particles, and it took 12 minutes to calculate the 3 seconds of footage that you see. This is a demonstration of two molecular spheres colliding into each other. This real-time simulation is pretty cool, but not much happens when they collide. There are only 1,232 particles in this simulation, and it was actually calculated in slightly less than real time on my computer. But some more powerful computers could calculate it in real time easily. This is my favorite simulation. It's the same as the last one with significantly more dense spheres colliding. This results in a spectacular collision that launches particles all over the screen. A slow-mo version of this video will play to show you the detail in the collision. This simulation has about 15,000 particles, but the physics have to be calculated 1,200 times each second in order to achieve an accurate result. It took around 20 minutes to calculate this simulation. Many of these simulations, though, are not what would be simulated in the real world. There's no reason to throw two molecular balls at each other. So I've constructed some real-world simulations so you can see what it might actually be used for. The first simulation is similar to the towers I destroyed earlier, but this is a more realistic demonstration with constraints that tie together the individual bricks in the house. You can see first a baseball hits the house, then a brick hits the house, followed by a bowling ball. And lastly, I swung two giant wrecking balls to destroy the house. This demonstration could be scaled up to any scale that you desire, even as big as the Twin Towers. I also created some different wind tunnel experiments. These experiments used 350,000 particles to simulate a fluid. I calculated why this would constitute as big data. This experiment required 5.88 quadrillion flops to simulate the 10 seconds of wind tunnel. The industry standards are significantly larger and more accurate than this, however, I did what I was able to. In my experiments, I simulated a torus, what many people will recognize as a donut, two cones glued together, and also an airfoil that I created. All of these experiments gave some interesting results. To recap, we learned about computational physics to start, then we talked about rigid body physics. We also talked a bit about soft body physics. And the most fun part, we watched a series of examples that demonstrated the difference between real-time and big data physics. Although the big data examples are not nearly the size that many big data physics simulations are in the real world, it was still an accurate demonstration. I even showed you some of these real-world possibilities with computational physics. So thank you for watching this video. I hope you had as good of a time watching the demonstrations as I did making them.
Okay, great. So this is a very special student. I mean, he is a computer science student. And what's amazing about this is that when he started working on our project, he didn't know anything about Blender. And you see all the simulations in the video. Those were all done by the student, basically. So once you get really engaged and once you become very passionate about especially topic in data science, I think you can definitely see what could be possible in this case.